I want to give you a very brief overview over the research we're doing in my group, the Solid State Quantum Optics group. And when I was preparing these slides, I was reminded of this quote here by Yoda in Star Wars: The Empire Strikes Back. And I actually disagree with this quote a little bit, and I hope that over the next couple of minutes I can convince you that we can really accomplish astonishing things if light and matter actually work together. So in my group, we're interested in the properties and the interactions of light and matter on a quantum level. So the interactions of single particles of light, photons, with single atoms or defects in a variety of solid-state systems, really. And on the one hand, we want to use light to control the state of atoms or defects. But on the other hand, we also want to use these matter-based systems, these atoms, to really control the properties of light, and even go one step further and use these matter-based systems to mediate interactions between multiple particles of light to make them do things light would normally not do. And what are those things? Well, they can actually be illustrated quite well by this picture here of these two gentlemen settling a galactic dispute with a lightsaber duel. And the lightsaber is really a remarkable science fiction item if you think about it, because somehow they managed to stop a beam of light right there in midair. And also these two beams or blades bounce off of each other, which is obviously in stark contrast to what we are used to in everyday life. My laser pointer here can in fact reach the screen, and it also doesn't interact with the photons coming from this projector here, for example, which is probably good, because otherwise I would probably create a huge mess by pointing at things, right? Nevertheless, these are exactly the two things that we want our photons to do in the lab, kind of. So how do we do this in the lab? Well, we have these special crystals here, and in our lab we typically have them mounted to a cryostat because we have to perform our experiments at very low temperatures. And these crystals can be made out of a variety of materials. A system we work with a lot is synthetic diamond, which, as you might know, in its pure form only contains carbon and is highly transparent. But other elements like silicon or nitrogen can either replace carbon atoms in the crystal lattice, or they can form more complex defects, like, for example, an atom sitting in between two missing carbon atoms. And these crystal defects strongly interact with light and are in fact what gives some natural diamonds their color. And these are the quantum systems that we use to really control our single photons in the lab. So how do we do this? Well, we can, for example, send a single photon into this crystal together with another, in this case, strong control pulse. So this is a light pulse that contains many photons at a slightly different wavelength compared to the single photon. And in fact, they are both at very specific wavelengths with respect to the internal energy level structure of our atoms or defects in this crystal. And in this special configuration here, our single photon is then mapped into a coherent excitation of these defects in the crystal, and we call this a spin wave. And coherent in this case means that the quantum state this photon was in is actually preserved and is now encoded in this excitation of the crystal. And then the cool thing is, if we send in a second control pulse, we can actually convert this excitation back into the original photon in its original quantum state, and it just continues its journey. So we've effectively stopped a photon in this crystal and then released it again on demand. So what we've effectively built here is an optical quantum memory. Very similar to a memory in a classical computer, but in this case for a quantum state. So this is stopping light. What about making it interact with other light? Interestingly, if we send a second photon through this memory without a control pulse, but while there is already a photon stored in the memory, then this photon will actually change this excitation ever so slightly. And if we then read this original photon out of the memory and compare its properties with the properties before it got read into the memory, then we see that they are now not identical anymore. Now they don't quite bounce off of each other, but they acquire a phase shift. It's a very minute change, but it's enough for us to then, for example, conditionally route them down a separate beam path just using passive optical elements. So what is all of this useful for? Certainly not building lightsabers, but building quantum computers, which you've probably heard of at this point because they've been all over the news over the past couple of years, including these gems of headlines here. Now, in the classical computer, information is encoded in bits, which can take on two states, 0 and 1. The building block of a quantum computer is the quantum bit, or qubit, which can also take on these two states, 0 and 1, but in addition to that, also arbitrary superpositions of 0 and 1, which we typically illustrate by these spheres. And then in addition to that, two qubits can also be entangled with each other, which means that they are in a correlated state where a measurement on one qubit determines the state of the other. And these two properties are the properties that we can really use to tackle a number of computational problems with quantum computers that cannot be efficiently solved on classical machines. The problem is that these quantum bits themselves need to be single quantum systems, which we need to be able to control precisely, and which should also not be perturbed by interactions with their environment, for example, too easily. And it turns out that photons are actually really good qubits in principle, because they do not interact with anything, even under ambient conditions, and we can encode quantum information in photons in many, many different ways. The problem is we can only really create them somewhat probabilistically, and they don't interact with anything, including other photons. So realizing logic gates between photons is actually very difficult. But our quantum memories can now actually solve all of these issues. So we can use our quantum memories to synchronize probabilistically created photons with each other, and then also use these memories to mediate interactions between these photons to actually perform purely optical quantum computation, and then also store the result of this computation in a quantum output buffer. And this research really relies on a very close collaboration between the materials development, because we need these special crystals, and the quantum optics side. And this is why we joined forces with Shannon Nicely's group in the ECE department here, who's currently setting up a diamond and quantum materials group. We have shared lab facilities and meetings, etc. And we sort of united our efforts under this joint umbrella of the Quantum Optical Devices Laboratory. So we are currently setting up a state-of-the-art quantum optics lab in the basement of the BPS. And Shannon is also building, for example, this chemical vapor deposition system for diamond quantum materials growth. Not only that, and we're starting to see first results on both the materials development side and the device fabrication side, sort of in preparation for first optical experiments, hopefully in a couple of weeks from now. So the lab is in a pretty good state already. Not only that, we also have the Fraunhofer USA Center Midwest Division for Coatings and Diamond Technologies on campus. And they have even more diamond growth, fabrication, and characterization capabilities on campus. And Shannon and I are both affiliated with the center as well. So I really don't think I'm exaggerating if I say that we've created a really unique environment and infrastructure here to do this kind of research. And I think it's pretty unique, not just in the US, but probably worldwide. And none of this would have been possible without the generous support by MSU and Fraunhofer, of course, but especially it would not have been possible without the support by you, Randy, and the Cowen family. And we're incredibly grateful for the support and grateful for the opportunities this now really opens up. And then last but not least, none of this would be possible without the people who actually do the work, our students. And even though both of our groups are still young, we've already been able to assemble an amazing team of students, and we're really looking forward to working with them over the next couple of years. Thank you.